So this is the Excel worksheet that illustrates the elementary Fourier Optics model for interferometers that measure surface topography. It's pretty easy to use. There are a few fields here where you can change the object. There are some fields here where you can change the optical system. There are some reported parameters when you change these others, here and here, and then of course there are these graphs, and we'll take a look at these one by one. Let's go over here and take first a look at the period of this sine wave for this object, and let's change that to 5 microns from 10 microns. You see the spatial period has changed, and the measurement result has gotten a little bit smaller, and if we keep going in that direction, we will gradually attenuate the signal. As we get closer in spatial frequency to the Abbe frequency limit, which is here, and that represents these points on the transfer function curve, and these are the diffraction orders that have to be captured by the transfer function. So if we change this period to 1, then we now have gotten to the edge and we don't see anything. So that's well understood. So let's go back to our original signal with the measured height here now looking good, and let's change the amplitude instead of the period. So we've changed now to 100 nanometers, and at 100 nanometers we got a good strong measurement result. It looks actually almost identical to the original, even better than when we had the smaller amplitude. And if we keep going, things look okay, but over here you see in the difference plot that we're starting to get some nonlinearity. This is plus or minus 20 nanometers of nonlinearity. And that's because you've got all these diffraction orders, and you've got to capture all of these diffraction orders inside the transfer function curve in order to get a faithful result. And the slopes here are so high that we're actually approaching 0 signal level. So if you really did this in an interferometer, you would start to see some dropouts at the high slopes. Matter of fact, if we keep going, the worksheet will flag that you have exceeded the slope acceptance of the instrument. And that's determined by the numerical aperture. So what are you going to do? You swap out the objective for one that has a higher numerical aperture, probably a higher magnification, and now you can get your signal back, and the nonlinearities are under control. So that's a reason why you might want to use a higher magnification objective, even though the spatial period is 10 microns, pretty easy to resolve. You need the numerical aperture in order to get a good result. Okay, let's go back down to 0.01 and try something else. Let's look at the twin post height. So we'll change the amplitude there. And when we do that, it turns red. That's because we haven't put the sine amplitude to 0. So I'll put the sine amplitude to 0. Let's increase the magnification a little bit by changing the field of view. Let's bring those posts a little bit closer together. And you can see there's some blurring here, and that's expected because it's an optical system. There's some limits. Matter of fact, if you defocus the optical system, that's not going to get any better. It's going to get worse. So let's bring it back into focus. There. And now let's see how close together we can bring things. Well, we already know the limit for an optical system is 1.22 microns in this case. Well, what about an interferometer? Well, you're going to see it's actually pretty close to the same thing. We'll come over here to the period. We'll change that to 1.22. We'll then magnify by changing the field of view. And we have this behavior that looks very much like the sort of Rayleigh criterion limit, but this is surface topography instead of intensity, but it does kind of follow that pattern. Where it's different from an ordinary optical system is if we change the amplitude here to 80 nanometers, the attenuation has increased. The relative attenuation has increased, and that's a characteristic of surface topography measurement, not of conventional imaging, and it has to do with these extra diffraction orders which are lost. They fall outside of the transfer function. So let's not do that. Let's go back to where we were. And let's be greedy. Let's see if we can go to half a micron. Well, we can't. It's now just one blur here. And maybe you could figure this out with a deconvolution algorithm. That would be super resolution. If you know that you have 2 posts here, maybe from the shape of this thing you could figure it out. But the model does predict that under those circumstances, half a micron, you're just not going to see it. Okay, let's go back to the very beginning. This is where we started, and that'll kind of conclude the introduction to the worksheet. I hope it's useful to you and you find it interesting. If it is, then maybe make your own model based on this, or come up with a model which is better, which is not too hard. But at least this is a starting point. All right. Thank you.